Hello everyone, welcome to this video tutorial. This is the first part of the Engineering Electromagnetics problem solving course. In this series of videos, I am going to solve all end chapter problems of this great reference, Engineering Electromagnetics. Here you can see the content, yes, the chapters of this reference. So the aim is to solve all in the chapter problems with details, and not only solving the problems but also using the MATLAB software to visualize data, to visualize geometries and solutions, right? For better understanding the concepts of this important course in electrical engineering. Okay, so before solving the problems, you should read the chapter. Okay, so first you should read the chapter and then come back to this video to solve the problems one by one. During the solutions, solving the problems, I also review, right, the content of the chapter. Okay, but it's better if you read the chapter first, right, solve the examples of the chapter, then come back to this video. Anyway, let's start by solving the first problem of the chapter 1, vector analysis. The chapter 1, yes, that is before starting physical concepts, right? This is mathematics for starting this course, electromagnetic. The next chapter is Coulomb's law and electric field intensity. Anyway, so the problem 1, if A represents a vector of 2 units in length directed due west, B represents a vector 3 units in length directed due north, and A plus B equal to C minus D, and 2B minus A be equal to C plus D. Find the magnitudes and directions of C and D. Take north as the positive y direction. Here you can see directions. We have west, east, north is the positive y direction, and here is the south. Coordinates of the A and B vectors are given. Okay, the A is -2 and 0. We have two-dimensional vectors in this problem. The vector A represents a vector of 2 units in length directed due west. Okay, this direction, negative x direction. Let's review some definitions. Cardinal points, right? That we have north, south, east, and west. These cardinal points are used for orientation and to express directions. Here we have the direction of the rotation for the earth, right? The direction of the rotation is from west to east. East is the direction in which the earth rotates. The west is the opposite direction of the earth rotation. And here we have these two definitions, the North Pole and the South Pole. Okay, so According to these cardinal points and these definitions, we can write these two vectors for the A and B. Anyway, we have two unknowns, two vectors, C and D. Each of them has two coordinates, Cx and Cy, Dx and dy. So in total, we have four unknowns, Cx, Cy, Dx, and dy. So let's use the first equation, a plus b is equal to c minus d. This equation we can write cx and cy minus dx and dy. We have pairs, two-dimensional vectors, is equal to this one. Also, you know that when we sum two vectors, we sum all coordinates separately. This is a vector summation, not a scalar summation. In MATLAB, we define vectors like this. This is a row vector, for example, A, 5, 6, and 8. If you write this in the command window, we will have a vector like this. You can check the size of A, that is 1 by 3. This is a row vector. Also, you can have a column vector, A transpose. So what is the size of A transpose? Is 3 by 1. This is a column vector. If you define A like this, 8, so this is a scalar variable. Size of A is 1 by 1. So if I have A, 5 and 6, B equal to 7 and 8, what is A plus B? We sum up the 5, right, with 7 and 6 with 8. That is 12 and 14. So we sum up all elements, right, one by one. This is element wise summation, right? Also, we have element wise product in MATLAB. So this is A, this is B. If I define this product dot a star B, so this is element wise product. What is the result of this expression? Is 35 by 48. 5 times 7, 6 times 8. So this is element wise product. So yes, here we have this system of equations. We have element wise summations, and this is the next equation. C plus D is equal to times B minus A, this one. So finally, we can construct these two system of equations. So here, Cx minus dx is equal to negative 2, and Cx plus dx is equal to 2. So if you sum up these two equations, yes, we can cancel out dx, and 2 times Cx is 0. So Cx is 0, and we can use one of these equations to find dx. So if you replace cx0 in this equation, dx will be equal to 2. So we have found the x components of the c and d vectors. We can do a similar computation to calculate cy and dy. Cy minus dy is equal to 3, and cy plus dy is equal to 6, right? This one. So if you sum up these two equations, we have 2 times cy is equal to 9 and cy is 4.5. And if you replace this into this equation, okay, you can calculate the value of the dy. That is equal to 1.5. Okay, not negative 1. So let me modify this equation anyway. The value of the dy, if we replace the cy 4.5 in this equation, yes, the value of the dy will be equal to 1.5. And finally, we can write these vectors using unit vectors. We can denote C, the C vector, using this notation. This pair of numbers, or 4.5 times AY. AY is a unit vector in the direction of the y-axis, or 4.5 times y hat, or 4.5 times j. You can use different right names. If you consider this x and this y directions, we can denote the unit direction in the direction of x, this one ax, or x hat, or I. Different notations are used. In our reference, the ax, ay notation is used to denote the unit vectors in the directions of coordinates. Here is the notation. For example, ag is the unit vector in the direction of the vector g. Components divided by its amplitude. This notation. So, also, you have the solution of odd problems at the end of the reference. Yes, this is the solution of the problem 1. So, this is the value of the d. Find the magnitudes and directions. We found the directions and we can calculate magnitudes. Yes, in this case, the magnitude is 4.5. And for the d vector, the magnitude is sqrt of the elements to the power 2, the summation of the elements of d to the power 2. So square root of 2 to the power 2 plus 1.5 to the power 2 is 2.5. Not too complex problem, right? The level 1. Okay, so the level of the problem is denoted by this, right, thermometer here. But let's solve this problem in MATLAB. However, this is a simple problem, but we can write code and learn how to solve problems like this in MATLAB. So define a new script. I am going to solve these two systems of equations. Cx minus dx equal to -2. So let's write a comment line here. Cx minus dx equal to -2, and cx plus dx is 2. This one. Cx plus dx is 2. So yes, we have this system of equations in matrix form. We can write it like this. We have these two variables, cx, dx. This is the right hand side is -2, 2, 1, -1, 1, 1. Okay, these equations, we can denote it in the matrix form. So this is the matrix, we can call it K any matrix. This is B. We know that Cx and Dx is equal to K inverse B. Okay. So in this case, I can define this matrix K like this: 1 and negative 1. The next row is 1 and 1. When you define a matrix like this in MATLAB, yes, you have a matrix with 2 rows and 2 columns. You can extend this matrix and write more elements here. So this is the way that you can define a matrix in MATLAB. You can define it like this also. The first row is 1 and negative 1. Then use the semicolon, and the next row is 1 and 1. So this is another way of definition of a matrix in MATLAB. What is the size of the K? 2 by 2. So here we have this matrix. The B vector is equal to negative 2, 2. We need to have a column vector. Yes, we need to have a column vector for B. So here simply I can write inverse of K times B. The solution Cx is 0, okay, and Dx is 2. This is right one method, but we have a simpler expression in MATLAB to solve this problem. Yes, when we divide two numbers, we write, for example, 7 divided by 8. This means that we multiply 7 by 1 divided by 8, or this is equal to 7 times 8 to the power minus 1. Can we extend this idea to have a general product? I mean, suppose we have this 7 this time backslash 8. So we have something like this: 7 to the power minus 1 times 8. Yes. So we can use these notations in MATLAB, these expressions. If you write, let's say 4 divided by 8, this is 0.5. But if I write 4 backslash 8, this is 2, because this is 4 inverse times 8. Yes. So instead of real numbers, we can use matrices. For example, if you have matrix A and matrix B, you can multiply these two matrices, or you can write A divided by B. So this means that A times B inverse, or if I write A backslash B, this is A inverse times B. So this is a powerful command in MATLAB, and we will use it multiple times when we solve larger problems in the next chapters. Okay, so let's learn the MATLAB step by step. We will solve these simple examples, and we will use these expressions for more complex problems. Here, if I write this K backslash B, I can solve the coordinates, right, of Cx and Dx, the solution vector. So this is problem 1. Let's save the M file. You can see the solution 0 and 2. So This is solution for x coordinates. And what about the y coordinates? We have these two equations. Cy minus dy is equal to 3. Cy minus dy is 3. Cy plus dy is 6. Okay, this equation. So we can define these two matrices. This is K again, and this is 3 and 6. So this solution for the y. Solution for the y. 4.5, 1.5. So finally, we will have these two vectors C that is equal to, we can define row vectors or column vectors. This is equal to solution X, the first element of the solution X, and the first element of the solution Y. Okay? And what about D? This is D, the solution X, the second element. This is solution X. We can pick up the first element of a vector in MATLAB, or an array in MATLAB using this. This is the second one. So yes, here we have C and this is D. These two vectors. How we can calculate amplitudes? We can write a command like this. We can use this notation. The amplitude is equal to a square root of the first element of the D to the power 2 plus the second element of the D to the power 2. So this is the first case. Yes, the first type. The amplitude of the D is 2.5. Or we can use this. We can use this line of the code. I can element wise, right? Power up all elements of D to the power 2, D to the power 2. Here is the D vector. If I write D to the power 2, I get error. And if I write D dot, right, to the power 2, we have element wise power up for all elements. And I can sum up D to the power 2. Finally, I can use this square root of this expression, that is 2.5. So this is another one, another case that we can find the amplitude of the D vector. So what is the next one? Simply we can use the norm function, norm of D. Okay, so here if I write norm of D is 2.5. Use the MATLAB built-in function to find a norm of the vector or amplitude of the vector. So here I write this one to use this built-in function. Yes, we have access to many good built-in functions in MATLAB. We can use them to solve the problem, to visualize solutions, and learn concepts much better. So this is the amplitude of the D, and amplitude of the C is normal the C. So let's run these two lines. This is the amplitude of the C and amplitude of the D. Anyway, yes, we learned this type of coding in MATLAB. Let's go for the next problem. Problem 2. Vector A extends from origin to 1, 2, 3, this point. And vector B extends from the origin to this point. Find the vector, the unit vector in the direction of A minus B. B, the unit vector in the direction of the line extending from the origin to the midpoint of the line joining the ends of A and B. So we have two vectors. We have these two vectors. This is the coordinate axis. We have three-dimensional vectors, but let's consider this 2D case. We have this vector A. We have the coordinate of this point, and this vector B. We have the coordinate of this point. So this is the vector A, 1, 2, 3, and this is the vector B, 2, 3, and minus 2. How we can calculate the unit vector in the direction of A minus B, this vector, okay? This is A minus B, the unit vector. We can calculate this vector and the unit vector A in the direction of A minus B is equal to A minus B divided by the amplitude of A minus B. Okay? So this is the vector A, this is the vector B, the minus, we can write, do element wise operation. This is a minus 1, 1 minus 2 is minus 1, 2 minus 3 is minus 1, 3 minus negative 2 is 5. So what is the amplitude of this vector? Is minus 1 to the power 2, minus 1 to the power 2, 5 to the power 2. The summation, okay, square root of this summation is 3 times square root of 3. So the unit direction in the direction of the A minus B, the unit vector is equal to this one. You can simplify that. So in MATLAB, we can write this code, the problem 2. Okay, this is the vector A is equal to 1, 2, 3. The vector B, 2, 3, negative 2. This is 2, 3, negative 2. So the A minus B, let's write it like this. This is A minus B. Let's write this comment. A minus B is equal to a vector from the B to A. Yes, this vector from the point B to the point A. So I can write this BA is equal to A minus B. So this is the BA minus 1, 5. And the unit vector in this direction is BA divided by norm of BA. Okay, so let's run the code. We have this unit vector. Exact numbers in MATLAB. We calculate this 3 times square root of 3. How we can visualize vectors? We can use this function is available in MATLAB. If we have a vector in For example, xy plane, this one, suppose this is the point 1 and 1, and we have a vector with this 1 by 2, the components of this vector, we can use this function, quiver function, to visualize this vector. So here we should write 0 and 0, 1 and 2. Yes, this point, excuse me, 1 and 1 and 1 and 2. We can denote this vector. If we have multiple vectors, we can use this type of the code. I want to show this vector and this vector at the same time. So the base of this vector is 0 and 0. Its x is a -1 x component and y component is 1. So I can close all figures first. I can plot this vector and hold on the figure to add this vector also to it, -1 and 1. In this case, we have these two vectors, a and b. Okay, or we can plot these two vectors simultaneously. That is possible. Okay, if we extend these vectors. So for this is for two-dimensional vector, but for three-dimensional vectors, we can use quiver 3. Yes. So this is the A, for example, in this problem, 0, 0, 0, 1, 2, 3. This is the vector A. And we have this in 3D space. The vector B is equal to 2, 3, -2. So I need to hold on the figure first and then plot the B. 2, 3, and -2. So this is the vector B, okay? And this is the vector A, these two vectors. Also, you can write text in this figure. You can use text. So let me write the code here. Visualize vectors. So let's use this code first. This is quiver A. Hold on the figure. And quiver 3, this is for B. Okay. Quiver 3, 0, 0, 0. The x, y, z coordinates of the origin. We have A1, A2, and A3. A2, A3. Similarly, we have this for the B. Okay. So you can see these two vectors. Here, as you can see, the scale of x, y, and z axis are not the same. So this is not a good visualization. I can use this line of the code, axis equal, to make the sizes equal, right? To use real sizes. So this is from 0 to this point, 0, 1, 2, 3, right? The x size and y sizes. So you can set the labels x label equal to x axis. We can set labels of x, y, and z. The y label and z label. Yes, this is z, this is x, and this is y. So this is much better. Okay, visualization for the x, y, and z. So as you can see, the x size here for the x, the vector a, the vector b is equal to 2. The x size is 2. The y size is 3. So this is the x size and the y size. So you can visualize it. You can check the labels also. How we can add text? We have this function in MATLAB, text, to add a text to a figure. So this is the coordinates. I want to write this text in the middle of the vector A. This text, let's try. This is the A vector, okay? And this text in the middle of the vector B, this vector. You should specify x, y, z coordinates and also a string variable to specify the vector. This is the vector A and this is the vector B. Now let's plot the BA vector. BA vector is different. First, we need to specify x, y, z coordinates of this point for the a minus b vector and then specify coordinates. Okay, so this point is actually b, coordinates of the point b. So here I can copy this b1, b2, b3, and these are ba coordinates. So here we have this. Okay, and if I write this, okay, text in the middle of this vector, in the middle of this vector, this string, I can denote it better. So here, let's check the A and B points. We need to have the summation. Okay, so let's comment this line. This is the A vector, B vector, but this is the BA vector. So why the B vector is not exactly right on this point? We have a property in this function, in this quiver function. We should adjust that property to get a correct plot, to get a correct figure. And let's check the help quiver 3, the properties of this function, the scale. Okay, so you can set the arrow scaling. If we set the scale of this property, I don't want to use auto scale in this quiver function. So I can plot vectors with their real amplitudes. This scale is important when you generate a vector field and you have lots of vectors. For example, this case, let me write plot this, for example, let's run this M file. We will generate these animations later. Okay. So when we have a vector field like this, we have many vectors and we can use them with a unified scale, right? Just for better visualization. But here in this case, we don't have, right, many vectors, just we have three vectors. And I set a scale off to plot the real values. So here for this quiver 3, how we can set the scale? Okay, simply you can write the value of the scale here. Okay, x, y, z, u, v, w scale. We can set a scale off, or if you write 0, it means off. So let's off the scales, and we have real amplitudes. So this is the vector b, the vector a, and this is the ba vector, or a minus b. How we can find the middle point of this vector? This is the next part of the problem. The part B. The unit vector in the direction of the line extending from the origin to the midpoint of the line joining the ends of the A and B. The middle point here for this vector, the A minus B, is this one, right? How we can find this vector? You know that this is A plus B divided by 2. Okay? So the vector C, this vector, C is equal to A plus B divided by 2. So we can write 1, 2, 3 plus 2, 3 minus 2 divided by 2. This vector, we can calculate the amplitude and finally find the unit vector in the direction of the C. Okay, this vector, we can calculate that. So in MATLAB, you can write this: C is equal to A plus B divided by 2, and the unit vector in the direction of C is C divided by norm of the C. So let's run the code. This is the unit vector in the direction of the C. And also let's visualize the C vector. Here I can copy this from origin to coordinates of the C. Okay. And finally use this text C1 divided C1, C2, and C3. Okay, this is A minus B. Yes, this is the A minus B vector, the A vector, and B vector. This is the vector C. Also, we can plot the unit vectors that we calculated. How we can plot the unit vector in the direction of the C? We can use this function, the unit vector in the direction of the C. Let's set the line width equal to 3 to denote unit vector better. So, or 2. This is the unit vector in the direction of the C. Okay. So when I zoom, as you can see, the figure is clipped. Here we can write this: set get current axis clipping option. We can make it off. clipping the axis. So when I zoom here again, you can see the vectors. Yes, the A, B, and C. You can zoom on this figure. This is the unit vector in the direction of the C. Also, we can plot the unit vector in the direction of the A minus B, this vector. Okay. Yes, good visualizations in MATLAB. You can use this type of the coding. Okay. How we can plot the unit direction in the direction of the BA. I can copy this line here. This is the unit vector in the direction of the A minus B. Let's increase the line width size for this vector. This is A minus B, the unit vector, and this is the unit vector in the direction of the C vector. Yes, you can use this notation also for the C vector. Okay, this notation for the C in the middle of the C vector. Yes, this is the vector C, A, B, A minus B, and these two unit vectors we calculated in this problem. Okay, this is good. You can write this M file in MATLAB and try to visualize the solution of this problem. Let's go for the next problem. Problem 3. The vector from the origin to point A is given as 6, -2, -4. This is the point A. And the unit vector directed from the origin toward point B is this one. If points A and B are 10 units apart, find the coordinates of the point B. So this is the problem. We have coordinates of the point A. Okay, so this is the vector A, and we have x, y, z coordinates of this point. And we have this point. This is the point B. We don't have coordinates of the point B, but instead we have the unit vector that is in the direction of the B. This vector. This is UB. The unit vector in the direction of the B. We have this vector. So if we have the amplitude of the BA vector or AB vector, we know that this distance is 10, okay, is given in the problem. The points A and B are 10 units apart. Find the coordinates of the point B. So we know that the B vector is equal to its amplitude times the unit vector in the direction of the B. Yes, this is the B vector, this is its amplitude, and this is the unit vector. So here we have A vector, the B vector is its amplitude times this unit vector. Let's check, is this a unit vector or not? In MATLAB, let's generate a new M file for the problem 3. Let me save this M file. This is the vector A is equal to 6, -2, and -4. Here we have a typo error. This is -4, 6, -2, and -4. This is B. So negative 4. This is U in the direction of the B is equal to 2 minus 2 and 1 divided by 3. So let's run this M file. This is UB. What is the norm of UB? Is 1. Yes, this is a unit vector in the direction of the B. We know that the amplitude of A minus B is 10. The amplitude of the A vector 6, negative to negative 4 minus B vector, that is the amplitude of the B times this unit vector is 10. So we will have this equation. This is negative 4. This equation derived by the amplitude of A minus B. This is a quadratic equation. Okay. So if you simplify this expression, finally we will have this. Yes, we will have this, and if we solve this quadratic equation, we have two solutions, B1 and B2. The solution of the problem is that one that is positive, because the amplitude of a vector is a positive number. So this is the correct solution. And finally, we can calculate the vector B. Okay, that is this one. How we can solve this problem? Yes, solution of a quadratic problem. Ax to the power 2 plus bx plus c equal to 0. And when a is not 0, we have these two solutions. Okay, so these are three cases. In our case, we have two real solutions. One of them is positive and another one is negative. So this is not a correct solution because the amplitude of a vector is a positive number. So this is the correct solution. The main point of this problem is simplification of this expression. Okay, so just mathematics to derive this equation and solve it. How we can solve this equation in MATLAB? In MATLAB, we can do symbolic calculations. So here, if I define these symbols, symbol B or a variable X, okay? So if I run this M file, as you can see, the X is a symbolic variable in MATLAB now, and we can use it to perform symbolic calculations. For example, if I write this expression, this one that we derived, the amplitude of this vector is equal to 6 minus x. Here is actually b, the amplitude of the b vector. 6 minus 2 times x divided by 3 to the power 2, okay, plus this term minus 2, right, minus 2 plus 2x divided by 3 to the power 2 plus the last one minus 4 minus b divided by 3. In our case, x is b. This is the expression. Okay, so expression we can use built-in MATLAB functions to simplify this expression. This is the left-hand side. So I need to move this 100 to the left-hand side to simplify the expression. So here is minus 100, and we can expand this expression. This is the expansion of the expression. Or we can simplify it. So let me check. This equation is not the same as this one that I derived before. Here, this number is negative 4. Okay, type error. So yes, using MATLAB, simply we can simplify this symbolic equation. Okay, really good. We have access to these built-in functions in MATLAB, but in exam, you should simplify this expression by hand. Okay, so finally, how we can solve this problem, this quadratic equation in MATLAB? We can find the roots using the roots function in MATLAB. To find roots of this polynomial, what are coefficients? The coefficient of x2 is 1. The coefficient of x is minus 8 and negative 44. The coefficients of this polynomial in this pattern. So we can find roots. As you can see, we have these two roots, 11.7, 3.74. Again, we have a typo error here. So this is the correct solution. And finally, we will have this point B. Okay. So we have roots. I can write B here. Yes, this is B. So we should select the B1. So let's write here solution for amplitude of the B. The first one is correct. And B is solution of B. The first one times the unit vector in the direction of the B. Yes, this is the B vector. Okay, so here we have the B vector. You can do the calculations here by hand also. Let's calculate the norm of A minus B is 10, correct? That is given in this problem, and we derived this equation considering this condition. Also, you can visualize A and B like before. We can visualize A, B vectors, right? Similar to this one. And also we can visualize the unit vector in the direction of the B. The same code that we have here. So you can see the vector A, B, and the unit vector in the direction of the B. You can change the color, right? If you are not happy with this color here, you can change the color of this unit vector by specifying this property, the color. You can use the black K or other colors. You can search in the MATLAB help. Okay, so you can specify other properties here. For example, arrow, the head size of the arrow. Other properties, arrow scale, show arrowheads. You can see these properties here to make a good visualization for these vectors. So we solved this problem. Maybe also you can plot the A minus B vector. Okay. Anyway, let's go for the next problem. Problem 4. Let me check the solution of the previous problem here. 7.8, 7.8, negative 7.8, 3.9. Yes, correct. Anyway, you can check solution of the odd problems. Anyway, problem 4. A circle centered at the origin with a radius of 2 units lies in the xy plane. Determine the unit vector in rectangular components that lies in the xy plane is tangent to the circle at this point and is in the general direction of increasing values of x. So we have a circle. The center point of this circle is 0 and 0 is the origin of the xy plane and its radius is 2 units. One point of the circle is given, this point, and we should find the unit vector tangent to this circle at this point in the direction of increasing the value of the x. So here we have this x axis, this is y. We have this circle. Okay, the center point is 0. The x and y coordinates of a point on this circle is given a square root of 3 and minus 1. Here, this point. So a square root of 3 is the x size. Okay, and this is negative 1, the y component of this point. So for this point, we have two tangent vectors. One possible tangent vector is this one, and another one is this unit vector. So which one we should select? In the problem, it is mentioned that we should find that one that is in the direction of increasing values of x. So this one. How we can find this tangent vector? You know, for a circle, the tangent vector to a point on a circle is perpendicular to this radial vector. Okay, so we know the components of this r vector. We can find the unit vector in the direction of the r, and finally we can rotate it 90 electric degrees counterclockwise, okay, in this direction. So yes, this is the process. What is the coordinates of the r vector? This one, this purple one, is a square root of 3, negative 1 and 0. Its amplitude is 2, yes, the radius of the circle. And the unit vector in the direction of the r is r divided by its amplitude, this one. Finally, we can rotate this vector 90 degrees counterclockwise. You know that we have this transformation matrix. If you have a vector in xy plane, this vector, if we rotate it counterclockwise, suppose that the rotation angle is theta. Okay? In the counterclockwise case r prime, the rotated vector, is equal to cosine of theta minus sine of theta, and cosine of theta. This is the rotation matrix times r. Consider that r is a 2 by 1 vector. Okay? In the case of clockwise rotation, we have this matrix cosine of theta, cosine of theta, sine, and sine of theta, and negative of sine of theta. This is the case that we have clockwise rotation. So, in our case, we should rotate UR, the unit vector, in the direction of R 90 degrees counterclockwise. So if we have this vector x and y, what is the rotation matrix in this case? Cosine of theta is 0, theta is pi divided by 2, sine of theta is 1, this is negative 1, 1. If we multiply this by x and y, the rotated vector is negative y and x. Okay, so here we should have this tangent vector negative y, negative of 1 is 1 and square root of 3. Yes, this is the process. So how we can solve this problem using MATLAB? I generated this figure using the MATLAB software. I wrote this code and let's review it. First, I draw a circle in xy plane. Here, I consider this theta, or this t variable. Okay, I'm going to draw a circle first. This is the x-axis and this is the y. How we can draw this circle in MATLAB? This is a trajectory. Yes, we can define this parameter, this angle t, and calculate x and y coordinates of points on this circle. You know that x is the radius 2 times cosine of t, and the y is 2 times sine of t. Yes. So in this case, how we can define t? I'm going to change t from 0 to 2 pi, generate 100 points. Using this linear space function, we can generate equally spaced points between 2 points. For example, between 0 and 5, generate 3 points. Is 0, 2.5, and 5. Generate 6 points, right? Between 0 and 5. We have these points. We can, right, increase this number to generate equally spaced points. And here I generate points between 0 and 2 times pi, 100 points. So the x coordinate of these points is 2 times cosine of t, the y coordinate is 2 times sine of t, and r is the vector, the r vector we discussed here in this problem. So here I plot the x-axis and this is the y. Then I draw the circle. Okay. Then using this quiver function, I plot the r vector. We can calculate the unit vector in the direction of the r, the tangent vector after 90 degrees rotation. Then we can plot the r and t. Using this property, we can specify the head size of the vector for better visualization. This figure. Okay, so you can assign text to these vectors. This is UR, UT, and this is the circle. Using this logic, we can find the tangent vector on any other points of the circle. So you can modify these components and try new cases, okay, for this problem. Okay, so let's go for the next problem, problem 5. An equilateral triangle lies in the xy plane with its centroid at the origin. One vertex lies on the positive y-axis. A. Find unit vectors that are directed from the origin to the three vertices. Part B. Find unit vectors that are directed from the origin to the three sides, intersecting these at right angles. So here you can see the triangle. Okay, this vertex of the triangle is on y-axis, and we should find these unit vectors. These purple unit vectors are directed from origin toward nodes, and these red vectors are from origin to this edge. These vectors are perpendicular to edges. How we can find x and y components of these unit vectors? So here we have this x axis, and this is the y. Okay, the x and y. We have this triangle. Suppose that this vertex is on y axis. Yes, here we have another vertex and this one. We can assign tags. For example, this is the node 1, the node 2, and the node 3. We can assign this tag to this edge. This is edge 1 that is in front of the node 1. Edge 2 is in front of the node 2, and this is edge 3. This is the first unit vector, this one, the purple one. This is in the direction of the node 1. U, let's call this N1. So let me write this tag here, U N1. This is in the direction of the y-axis, the positive direction. So this is equal to AY. Okay, the unit vector in the positive direction of the y-axis. What about the unit vector toward N2? This one. Consider that this is an equilateral triangle. We know that this angle is 60 degrees. Okay, so this is 30, and this is in parallel with the x axis. So this is 30 degrees. This angle, if you consider this UN3, this angle is also 30. So we have the angle of these two unit vectors with respect to the x-axis. We can find x and y coordinates. What is the x coordinate of this unit vector? Is negative of cosine of 30. Negative of cosine of 30 degrees times the unit vector in the direction of x. The y component is negative of sine of 30. This is the y component and this is the x component. Okay? What about the un3? This is the x component, cosine of 30 degrees. The y component is negative of sine of 30 degrees. So this is the solution of the part A, these purple unit vectors. Also, you can check the solution here, solution of odd problems, problem 5. The unit vector is this one. So we should calculate the cosine of pi divided by 6, 30 degrees, 0.866, 0.87. Okay, the negative one. Also, you can calculate other components. Now let's solve the part B. Find unit vectors that are directed from the origin to the three sides intersecting this at right angles. This vector, for example, this red one. Okay, so this is perpendicular to E2, for example, or this one. This is perpendicular to E1. So this the unit vector for the first one, this is u, E1 is negative AY, okay, in opposite direction of the y-axis. This is simple. But what about this one, u, E2, the unit vector in this direction, we should find this angle. We can consider this triangle. Yes, this angle is 30. This angle is 60 because this is 90. Okay, so this is 30 and finally this is 30. We can find components of UE2 is cosine of 30, sine of 30. Okay, this one. And UE3 is this vector. The unit vector, we know this angle, this is 30. We can find the x and y components. Also, you can see the solution here for this problem. Okay, not too complex. How we can solve this problem in MATLAB? I generated this figure using the MATLAB software. So here is the M file for the problem 5 I wrote to save the time. We have these nodes. I considered the y component of the first node equal to 2 units. Okay, n1, n2, n3, the x and y components. So we can generate these two vectors to plot a closed polyline, a triangle. Okay, so what is the unit vector in the direction of n1? Is the right n1 divided by its norm. Similarly for n2 and n3, the unit vector in the direction of h1 is the summation of un2 and 3 divided by 2. Yes, this is a triangle that the length of their edges are equal, right? An equilateral triangle. So we can write UE2. This is equal to the summation of u n1 plus u n3 divided by 2. We should make this vector normalized, right? We should divide it by its norm. What I did here. Okay, so then we can plot the x-axis, the y, plot the triangle, plot the right vertex n1, vertex n2 and vertex n3. Yes, here I specified these properties to make a good image. Okay, so here I used quiver function to plot unit vectors. So if we run the code, here as you can see, we can generate the geometry of this problem. Perfect. You can try this code in MATLAB to solve this problem and visualize the geometry and vectors. So let's go for the next problem. Problem 6. Find the acute angle between two vectors A and B by using the definition of the dot product and the cross product. So we have two important definitions in the chapter 1. The dot product between two vectors and the cross product. The dot product is defined using this equation. You know that you checked the chapter 1. The dot product geometrically is defined as the product of amplitudes of two vectors times the cosine of theta, the angle between these two vectors, the acute angle. Okay, so we have this equation: a dot b is equal to b dot a. Commutative law, is true for the dot product, and operational definition is this one, using the xyz components of the vectors a and b. Okay, a dot b, this definition. So we can calculate this angle between these two vectors using this definition. This is a, b. So a dot b is equal to, here I use the operational definition, this definition. This is equal to 2 times 1, 1 times negative 3, 3 times 2, that is 6. The summation is 5. Yes? And if we use this definition, this geometrical definition, we can calculate the amplitude of A, the amplitude of B, and finally use this equation to calculate the theta. Cosine of theta is equal to 5 divided by 14. Theta is 69.1. What if we use the cross product? We know that the cross product of two vectors is a vector that is perpendicular to these two vectors. This is definition of the cross product. Okay, the cross product of A and B is this one. Okay, results in a vector. The amplitude of the cross product of two vectors is amplitude of A times B times sine of theta, the angle between two vectors. So for the cross product, the commutative law is not available, right? But instead we have this equation: B cross A is negative of A cross B. So this is important. Now let's use definitions, two definitions, the operational definition and the geometrical definition of the cross product to find the angle. This is the operational definition. Yes, it's complex, right? But instead, we can remember this equation using this formula. The determinant, of this 3 by 3 matrix. We have ax, ay, az, and here we have components of a and b vectors. So easier to remember this equation. So here we have this equation. Let's fill. This is the right components of the A vector 2, 1, 3. For the B, we have 1, negative 3, and 2. If we calculate the determinant, we will have this vector. So the amplitude of A cross B is this one. And finally, we can calculate the sine of theta, this angle. How we can solve this problem using MATLAB? So let's generate a new M file for this problem 6. Let me overwrite to this one. Here we have the vector A. This is equal to 2, 1, 3, 2, 1, 3. The vector B is equal to 1, negative 3, and 2. 1, negative 3, and 2. So what is the dot product? I can calculate the dot product of the A and B. The dot product is equal to, you know, here I can use this syntax. A, element wise product. B, we can calculate summation of this, that is 5. So the dot product is element wise product that we have in MATLAB. Yes, the dot product. Element wise, after that, we should use the summation function. So instead of that, let me check if this function is available in MATLAB dot A and B. Yes, dot product of two vectors. We can use this syntax, or easily we can use this function, the dot product of the A and B. So what is the theta AB, the acute angle between A and B vectors? Is the using this definition, dot product divided by amplitude of A, norm of A, times the norm of B. So this is cosine of theta. We should calculate A cosine, the cosine inverse. So this angle, if we multiply this by 180 divided by pi, this is equal to 69 degrees. So consider that we can have two cases. If this is the A vector and this is B, so the dot product of A and B is a positive number. Okay, consider 2D vectors. So A dot B is a positive number in this case. This is theta, and in this case the dot product is negative. This is A and this is B. So in this case the dot product is negative, and we calculate this angle. Okay, this angle theta in this case. So using the dot product, always we calculate the acute angle between two vectors. And what about the cross product? Yes, we will check that in one of the next problems. We know that the amplitude of the cross product A cross B, the amplitude is the amplitude of A times the amplitude of B times sine of theta. So if we have this A vector and this B vector, B, this is the acute angle. Also, this is B, right? Consider B prime, this vector. We know that the sine of theta is this one for this vector. And for this angle, this larger angle, the sine of theta again is this one. Yes? So we have two solutions, this angle and this angle. Two solutions for this cross product, we should select this one. Okay? So this is one ambiguity that we have for the cross product when we calculate the angle between two vectors. Anyway, yes, this is calculation using the dot product. And let me check the cross product. Do we have this function? Cross A and B. Yes, this is the cross product. So this theta is calculated using the dot product. And for the cross product, we can use this A sine of the norm, the amplitude of the cross product of the vectors A and B divided by their norms. So what is this angle? 69 again. Okay. So how we can visualize vectors? We can visualize vectors simply similar to previous M files that we wrote. Even you can plot the cross product. Anyway, up to you. Okay, good practice if you do that. So let's save the time and go for the next problem. Problem 7. Given the field F that is equal to x times ax plus y times a sub y, if f dot g is equal to 2 times xy and f cross g is equal to this one, find the g. G is a vector field, okay? And also f is a vector field. The z component of f everywhere is 0, okay? So let's consider only the values of f on xy plane. The dot product of f and g is equal to this one. The cross product is equal to this one. The cross product is always in the direction of the z axis. So we can guess that the vector field g, the z component of the vector field g must be 0. Okay? Because the cross product of g and f is always perpendicular to xy plane. Yes, we have a z component. So the z component of the g vector field is 0. In this case, we should determine gx and gy. We have two equations. So here are system of equations. F dot g is fx gx plus fy gy. This one is equal to 2 times xy, and f cross g is this one. So this is the cross product for two-dimensional vectors. So here, simply in this equation, you can multiply both sides by y divided by x. We will have this equation. Then if you sum up this equation with this one, you can find the value of the gy, that is x, and gx is y. This is the g, the vector field g. Okay, interesting how we can visualize these two vector fields. Let's generate a new M file for the problem 7. Okay. In this case, I am going to visualize these two vector fields considering a rectangle region of the xy plane. Yes. First of all, we should generate grid of points in xy plane. In MATLAB, we can use this function to generate a mesh grid. You know, in the linspace function, linspace, we change the value of x, for example, from -2 to 2, consider 10 points. So this generates a one-dimensional vector. But suppose that we are going to generate a region in xy plane. This is x, this is y, and I'm going to consider this region. Okay, so how we can generate these points inside this region in a 2D matrix form? Okay, so if we consider that we have nx points, this is the number of points in x direction, and this is ny, the number of points in y direction. In total, we have nx times ny points. Yes. So how we can generate? Simply using the mesh grid function in MATLAB. Mesh grid. We should specify range of x and range of y. So linspace, I want to change x from, let's say, -5 to 5, consider 10 points. And I want to sweep over the value of the y for the same range. The output is x and y. So if I run the code, in this case, x is a matrix, y is a matrix. We have xy coordinates of these grid points here in this case. Yes, sweeping over these two variables. So we can vectorize these coordinates. I mean, when we have a matrix in MATLAB like this, z equal to 5, 6, 8, 9, we can change the format of matrix and generate a vector using this vectorize command. So first we have the first column 5, 8, and then 6, 9, and so on. So after generation of the mesh grid, we can sort the data. X and y is equal to y column. Vectorize these two variables. So we have x and y coordinates of these mesh points one by one. Now we can plot this vector field using the quiver function. The x component is x, the y component is y. So f of x, this is x, f sub y is y. Yes, the vector field x and y components of the vector field f. So let's use the quiver function x and y, fx, fy. We can set the scale off or set the scale. Let's check. This is the vector field f. Okay. Let's set the axis equal. This is the vector field f. What about the g The gx is y, gy is x. Let's check. This is f, excuse me, gx, and gy is x. So let's generate a figure first and hold all plots in the figure. We can plot the vector field g using the quiver function. Yes. Okay, this is beautiful. The blue one is the f vector field, and this orange one is the g. What about the cross product? The dot product is given, and this is the cross product. We can calculate cross product. The z component is this one, x to the power 2 minus y to the power 2. So the cross product, let's call it C cross product. Only we have the z component for the cross product, that is x to the power 2 element wise operation minus y to the power 2. The cz, cx is 0, okay, everywhere. So how many points we have? The size of vectors must be correct when we are going to use the quiver function. In this case, we can find the number of points is length of the x vector. We know that cx is 0 everywhere, 0 number of points and 1 generate a 0 vector. The same for the y, okay, and the same for the z component, okay, the z coordinate of the points. In this case, we should use the quiver tree function x, y, z, cx, cy, and cz. Let's run, rotate the figure. Here you can see the cross product of these two vector fields, right? Perfect. We have three vector fields, x and y and z. Okay, is perpendicular to the xy plane. Yes, we can use these good built-in functions in MATLAB to generate these interesting graphs for good visualizations. The xy plane and this vector field, the cross product. Anyway, also we can add the XYZ labels and legend to the figure for the field F, field G, and F cross G. So if I run the code, here you can see the fields. The F is the blue one, G, and F cross G. Okay, these three vector fields that we have. Here also I had this type error. This is the Z component of the F cross G. Okay, these two vector fields. Anyway, now let's go for the next problem. Problem 8. Demonstrate the ambiguity that results when the cross product is used to find the angle between two vectors by finding the angle between A and B. These two vectors. Does this ambiguity exist when the dot product is used? Let's check. We discussed the concept that we have in this problem in this one. Okay, So let's calculate the angle between these two vectors using the cross product and dot product. We know that the cross product A cross B, the amplitude of the cross product is this one. Also, we can calculate the cross product using this formula. If you replace elements of the vector A here, 3, negative 2, and 4, the entities of the vector B, 2, 1, negative 2, this will be the cross product of the A and B. We can calculate the norm of this vector. 14 to the power 2, 7 to the power 2, the square root, the summation. So what is the amplitude of the A? Is a square root of 29. You can calculate that. The amplitude of the B is a square root of 9. Okay, that is 3. So the sine of theta is equal to this one. We have two solutions. Okay, we discussed this. When we have these two vectors, this is A and this is B. B times sine of this angle is this one. So here, in this case, let me call this is B times sine of theta. And the next case is this one. Consider this B prime and this angle. So B prime times this angle is again this one. So we have the same result. In this case, we have two solutions. Okay, so this is the ambiguity for calculation of the angle between two vectors using the cross product definition. But using the dot product, we can calculate the correct angle. Okay, so here the dot product is negative using the operational definition. So actually for this problem, we have this case. We have this case. This is the vector A and the vector B. You know that the dot product is negative and we can calculate this angle or cosine of this angle. Okay, is a negative number. Theta is higher than 90 degrees. Anyway, how we can calculate this problem using MATLAB? The problem 8. Here I wrote this code to save the time. This is the vector A, the vector B, the angle between two vectors using the dot product. And here is calculation of the angle using the cross product. Then I visualized these two vectors. So yes, this is the vector A, the vector B, okay? And we have these two numbers. This is the angle calculated using the dot product, 104. This angle, so 104.33 minus 180 is negative 75.6. This angle. And using the cross product, we have this one, this angle. Okay, so in this case, if we consider this is the amplitude of the cross product is 15. Okay, the amplitude of the cross product. Can I calculate the cross product using this function? Norm of A times norm of B times the sine of this angle, 75.7 times pi divided by 180. this number. Okay, this is one solution. Another one is 104.3. This is again the same. Okay, so we have two angles. But in the case of using inner product, only we find one angle. This negative one or this higher one, you know that. So yes, we don't have this ambiguity when we calculate the angle using the dot product. Okay, so I added this figure to this slide, and let's go for the next problem, problem 9. A field is given as G equal to this one. This is a vector field. Find a unit vector in the direction of G at this point. B, the angle between G and AX. This is the unit vector in the direction of the x coordinate at point P. Part C, the value of the following double integral on the plane y equal to 7. So we have a vector field and we have three parts in this problem. In the first part, a point is given, the point P. We should calculate the components of this vector field at this point. So here, this is G 25 divided by x to the power 2 plus y to the power 2 times this. So if we replace this number, P, the x is 3, y is 4, and z is negative 2. If you replace the numbers, we will have this vector. The z component is 0. As you can see, this vector field is two-dimensional. We don't have z coordinate or z component in this vector field. This is a two-dimensional vector field. The part B, the angle between G and AX at this point. So we have the value of the G at the point P. So what is its amplitude is equal to 5. Yes, you can calculate the amplitude of this vector. And when we calculate the dot product, what is the dot product of this vector by AX? Only we have this term, right? The dot product is equal to 3. So in this case, we can calculate the angle between the G at the point P and AX. Okay. Also, here I used this geometrical definition. Here, first I calculated the unit vector in the direction of the GP. The unit vector AX, its amplitude is 1. Amplitude of UP is 1. 1 times 1 times cosine of theta is equal to this dot product. Finally, we will have this. The angle is 53 degrees. So, this is the part B, not too complex. The part C, the value of the following double integral when the y is equal to 7 on this plane. When we set the value of the y equal to 7 in this equation, okay, we will have this vector field that is only a function of x. And what is the dot product of the resultant value by ay is this one. 25 divided x to the power 2 plus 49 times 7. We replace this expression into this double integral. We will have this. Okay? And finally, we should calculate this double integral. Okay? So we should calculate the double integral on this plane. Okay? the variation of dz is from 0 to 2, and dx is its variation is from 0 to 4. First, calculate the inner integral, not too complex because we don't have any z variable inside this double integral. Is 2 times this one, 25 times 7. Okay, so 25 times 2 times 7 is 350 divided by this. We should calculate this integral. Yes, this integral is equal to this one. You remember this integral here. We have these important equations. So the integrals and derivatives of important functions. You should remember these functions for the exam. Okay, what is our case here is this one, tangent inverse of x, the derivative of arc tan x is this one. So if you change the variable and use the tangent inverse function, its derivative, you can solve this integral. Not too complex, okay? So the final value is 26. Let's check the solution for the problem 1.9. Yes, the value of the double integral is 26. This is the angle and this is the solution of the part A. How we can visualize this vector field? Okay, so here in MATLAB, let me copy this code we used for the problem 8. We can visualize this vector field. So let's copy this, save as problem 9. Okay, to visualize this vector field, first we should generate a mesh grid. So the x coordinate of the point P is 3. I'm going to change the x from, let's say, point 2 to 4. Consider 20 points. The y is 4. So change the y from 2 to 6, 20 points. The value of the gx is equal to 25 divided by x to the power 2 plus y to the power 2 is 25 divided by x to the power 2 plus y to the power 2. Consider that we should have non-zero denominator here. I think we can consider x equal to, let's say, 0. Okay, or 1 to 5 is better. So we should make sure that this is non-zero. The x is this times x. Yes, here we have x times ax. The gy, this is y. So gx and gy, we can plot this vector field. This is the legend. Let's comment this. And now we can run this function. So here is the vector field. Why we have something like this? Let me check. The reason is this one. We should consider the dot, the element wise division also here. Okay, so this is important. Now this is the correct solution. the x-axis, the y-axis, and this is the vector field G. Okay, so now let's plot the value of the G at this point, 3, 4, and negative 2. Because the G is not a function of Z, I'm going to neglect this one. Okay, we can also sweep over the value of the Z. But because this is a two-dimensional field, we know that we have the same values when we change the Z component. Okay, the same cross sections. But if you are interested, you can change the value of the Z. For example, in a space here, let me change the value of the Z from negative 3 to 3. Consider 7 points. So this is Z, and here this is Z. The value of the GZ is equal to 0. Okay, so I can write here 0 times Z, or we can calculate the number of points, np, that is length of x, and generate a zero vector, zeros, np, and 1. Yes, this type of coding is better. Using quiver 2, I generate this graph, and using quiver 3, I generate a new graph, gx, gy, gz. The z label is z axis. So v and w must be the same size. Let me check. This is gx, gy, gz. This is x, y, z. Okay. What is the size of x? Yes. Here, np is actually the number of elements of x after vectorization. Okay. So, yes, this is the correct code. This is three-dimensional view of the field. We plotted the field on different cross sections. Let me reduce the number of points. Is not needed. Here, just consider 4 cross sections. Okay, for this 3D view, better visualization. You can imagine that. Okay, we generated graph for these 3Z levels. But because this vector field is not a function of Z, vectors are in parallel with the XY plane. This one. So again, let's increase for the 2D view. In this case, for the 2D view, how we can plot the G at the point P? The point P is equal to 3, 4, negative 2. I write 3, 4, and 0. Okay? 3, 4, and 0. I want to plot it on XY plane. So, yes, the value of the G for this point, the X is P1. Okay, we replace this, and the Y is P2. This is the Y. And this is the value of the gx for the point P and gy. That's all. We can use the quiver function. Let's set the color red to plot this point, the value of the vector field at this point. Okay, using this function. So yes, here you can see the value. Okay, we should use correct scale. Here, if I make the scale of, we have this vector field. You can see the value of the vectors are in real values, real amplitudes. But this function scales the vector to have a better visualization. For this point P, also we can adjust the scale. So if I write 1, this is the real scale. If I set the scale equal to point 0.3, let me comment this right part of the code. Here, as you can see, we can scale this vector. So this is the value of the vector field at this point G, and we calculated this angle, the angle of this vector with respect to x-axis, this angle in this part, okay, and so on. So you can write this code, redo calculations, and review the solution of this problem. Anyway, so let's go for the next problem, problem 10. By expressing diagonals as vectors and using the definition of the dot product, find the smaller angle between any two diagonals of a cube, where each diagonal connects diametrically opposite corners and passes through the center of the cube. So here you can see the cube. You can consider an arbitrary length for any of cube edges, not important. And here we have these two diagonals, A and B. These diagonals that pass through the center of the cube. We can suppose these two diagonals, or we can connect this vertex to this vertex. Okay, not important. So, how we can find the smaller angle between any two diagonals? In this case, I considered the A and B. The A here is the length of the cube edge. You can consider any edge. And the vector B is ax minus ay plus az. Here, if you consider this x-axis, this y, and this z. So again, we can use the dot product definition. This is the dot product using the operational definition, and this is using the geometrical definition. So the smaller angle between these two diagonals is 70.5 degrees. I generated this image using MATLAB. So let's review the code. I wrote this code to save the time. Here, the A is the length of one cube edge. I considered it equal to 1. Okay. And here we have XYZ coordinates of the cube vertices. Here is the cube. Let me run the code. This is the cube. Okay. So if I copy this image, this is the vertex number 1, vertex number 2, 3, 4. This is vertex number 5, 6. This is 7, and this is 8. Okay, we have XYZ coordinates of these vertices. Okay, so you can follow these 3 lines of the code, not too complex, just to generate the geometry of the cube. And I used this plot tree function to plot 3D trajectories. First, I plot the bottom rectangle, this one, 2, 3, 4, and this top one, 5, 6, 7, 8, and then I draw these four vertical edges. Okay, this is the syntax. So what is this syntax? X 1, 2, 3, 4, 1. You know, when we have a vector in MATLAB like this, 8, 6, 5, and 7, you know that Z1 is 8, Z2 is 6. If I want to get the Z1 and Z2 simultaneously, I can write Z1 and 2, 8 and 6. If I want to get Z1, 2, and again 1, this is the resultant vector, 8, 6, 8. So indices of a vector is also a vector of indices. Because I wanted to draw closed rectangles, I consider these vectors. Then we have these two vectors, vector A and B. The vector A, this one, connects the point 1 to the point 7. Okay, so how we can calculate coordinates is xyz coordinates of the point 7 minus xyz coordinates of the point 1. What about the b vector? B vector connects the point number 4 to the point number 6. So similarly, I can calculate xy components of the b. And here is the definition of the dot product. We can calculate the smaller angle. And here I visualize a and b vectors, okay, and assign tags and so on. So if I run this code, as you can see, the value of the angle between A and B is equal to 7.70.5 degrees. Okay, so you can rotate this cube to visualize these diagonals. Perfect. We can use MATLAB to visualize geometries, right? To solve this problem and learn the concepts. So I highly suggest you to write this code and try this example. Anyway, let's go for the next problem. Problem 11. Given the points M, N, and P, find the vector RMN dot product of RMN by RMP, the scalar projection of RMN on RMP, the angle between RMN and RMP. So not too complex. Okay. We have XYZ coordinates of these 3 points, MN and P. We can calculate RMN, that is Rn minus Rm. So actually we have these 3 points. This is the point M, this is the point N, and this is P. So here we have these vectors Rmn from M to N. This is Rmn, and this is Rmp. So yes, you know that you can calculate these two vectors using these equations, and we can calculate the dot product using the operational definition. That is equal to 0.05. Yes, the part B of this problem. The part C is the scalar projection of the RMN on RMP. So here we should project this vector on this vector. So this is the projection of the RMP on RMN. How we can calculate this vector? You know that First, we need to calculate the unit vector in the direction of Rmn. Yes, that is Amn, the unit vector. Then this vector is the Rmp, dot product of Rmp with the unit vector of Rmn times this unit vector. This is the right projection vector, and its amplitude is this one. So dot product of this vector on unit product of the vector that we are going to calculate the projection with respect to it. Yes. So if you have two vectors, a and b, we have two cases. Okay. So if we are going to calculate the projection of the b on a, this amplitude, we have this equation b times a, the unit vector in the direction of a. And this projection is a dot the a vector, the unit vector in the direction of the b. These two equations. Okay. So I think also we have these equations in this section of the reference. So you can review the reference carefully. Okay. Anyway, what is the next part of the problem? The angle between Rmn and Rmp. This angle theta, we can use the dot product definition. So using the dot product definition, we can calculate this dot product amplitudes of these two vectors, that is equal to 78 degrees. So here we have these solutions for the problem number 11. Let's check. This is the part A, the part A, okay, the vector Rmn, the part B 0.05, this number, the part C, okay, and this angle. So not too complex. We don't need to solve this problem in MATLAB. So let's save the time and go for the next problem. Problem 12. Write an expression in rectangular components for the vector that extends from x1, y1, z1 to x2, y2, z2, and determine the magnitude of this vector. So we have these two vectors, a1, we have these three components, and this is a2. So what is the vector that connects the point 1 to point 2 is a2 minus a1. That is this one. So how we can calculate the amplitude or the distance between the point 1 and 2 using this dot product definition. Okay, the amplitude of a vector is a square root of its dot product, right, with itself. So is this equation. This is the norm, the second norm of a vector, or distance between these two points, this point and this point, familiar, right, a well-known equation. So what is the aim from this problem? So you should, in the next chapters, when we calculate electric fields, magnetic fields, and forces, we use this notation R12, the vector from the point 1 to point 2, or the point I to point J. So this is this vector R I J, and RJI is the reverse one, is this vector. Okay, so you should know that the Rij is the xy coordinates, xyz coordinates of the point J minus the point I. This is a definition that we use it in next chapters. And we know that the distance, the amplitude of the Rij is equal to a square root of Rij dot Rij. Yes, these definitions that we have here. So let's go for the next problem. Problem 13. Find the vector component of f that is parallel to g, okay, this vector. B, the vector component of f that is perpendicular to g. And C, the vector component of g that is perpendicular to f. So, in this problem, we have these two vectors, vector f and vector g, this vector. So, considering the vector f, we can write the vector g, we can split it into two terms. This term, okay, and this term. So, this is actually, if I call this g1 and g2, we know that g is equal to g1 plus g2. So actually, we splitted the vector g with respect to the vector f. The g1 is the part of the g that is parallel to f, and g2 is the part of g that is perpendicular to f. Okay, so we use this separation also in next chapters when we calculate fields. So how we can calculate g1 and g2? You know that if we have a unit vector in the direction of f, g1 is equal to g dot af times af. Yes, this vector g1. And g2, the perpendicular part, is g minus g1. We can use also this notation. G1 is the g1 is the g that is parallel with f, and g2 is the g that is perpendicular to f. This segregation is important. So here we have these equations. The part A, f that is parallel with g is f dot unit vector in the direction of the g times the unit vector in the direction of the g. So how we can calculate this unit vector is g divided by its amplitude. So we can extend this equation. If we use this definition, replace it here and here, we will have this equation. F that is parallel with g is f dot g times g divided by the amplitude of the g to the power 2. So if you replace the vectors and calculate right these expressions, we will have this vector. How we can calculate f that is perpendicular to g, that is equal to f plus f minus f that is parallel with g, this equation. So we have counterpart calculations for the part C. How we can calculate g that is perpendicular to f is g minus g that is parallel with f. This definition, if you replace these vectors and do calculations, finally we will have this vector. So you can compare the solutions here for this problem 13. Okay, we will have these three vectors. Anyway, so let's solve this problem in MATLAB and visualize it to check calculations. It's good if we generate image for this problem. Here, let me save this problem. This is problem 13. Again, we have two vectors and we are going to visualize them, the vector A and B. So, what is the vector A? Components of the vector A. Excuse me, here we can use F and G. F is 10 minus 6 and 5. F is 10 minus 6 and 5. B is equal to zero point 0.1, zero point 0.2, zero point 0.3, zero point 0.1, zero point 2, and zero point 0.3. Here I wrote B because I want to change this variable now, G. And if we press Shift plus Enter, we can rename, right? B in the following expressions. We have these two vectors. So the F vector and the G vector. These two vectors, F and G. What is the unit vector in the direction of the G and unit vector in the direction of the F? The unit vector in the direction of the G and F. We don't need to calculate that. So let me plot F and G only. G is too small in compare with F. Okay? It's too small in this problem. So let me multiply the G by 5 just for better visualization, or 10. Yes, this is better. Okay? This is better. Maybe right. In this problem, we have 1 point. But this is not a good vector for visualization. And how we can calculate F that is parallel with G is parallel with G is equal to F dot G times G divided by amplitude of the G to the power 2. So dot product of F and G times G divided by norm of G to the power 2. Okay? And the next one, F perpendicular to G is equal to F minus this one. We know that. So now let's plot these two vectors. This vector, okay, and the next one, this vector, perpendicular. So let's run this M file. Here, as you can see, we have these two vectors, this one and this vector. Okay, so let me increase the line width. Line width equal to, let's say, 2. Yes, just for better visualization. Yes. So the vector F and the vector G, we write the F versus its component, its parallel component with G, and its perpendicular component to the g vector using this equation. So this is a 3D view. Okay, if I use the same number that is in the textbook, yes, we have this visualization, the G. Not important what is the amplitude of the G, okay? Because we are going to rewrite F versus its parallel component with G and the perpendicular one. So we can do reverse also. Write G versus the parallel and perpendicular components to F. Anyway, good problem. You can try this M file and generate this image. We will use these equations in the next chapters. So let's go for the next problem, problem 14. Given that a plus b plus c equal to 0, where the three vectors represent line segments and extend from a common origin. Must the three vectors be coplanar? If a plus b plus c plus d equals 0, are the four vectors coplanar? So let's answer to this problem. If we have three vectors a, b, and c in 3D space, okay? So this is the vector a, the vector b, and the vector c. We can consider the plane that is constructed with AB. You know that. What is the XY coordinate system? Actually, in XY coordinate system, we have this case, we have two unit vectors, AX, this unit vector, and this unit vector, AY. These two unit vectors are perpendicular to each other, and we write any arbitrary vector in xy plane using a combination of these two vectors. Okay, so this arbitrary vector with these components x and y, we write this vector r as this one, x times ax plus y times a sub y. Okay, this equation. This is one coordinate system, but not necessarily we need to have ax and ay to be perpendicular. So if we have these two vectors also, for example, ax and ay, again, we can write any arbitrary vectors in the plane that is generated by these two vectors, okay, using a similar equation. So, what is the perpendicular vector on the plane generated by these two vectors is ax cross ay. Okay, so as long as the angle between ax and ay is not 0, we can construct a plane. So in this case, suppose we construct a plane using a and b vector. Okay, so we can write any arbitrary vectors in the plane generated by these two vectors using a similar equation like this. So if we write this equation using coordinates, we can write ax plus bx plus cx times ax plus these terms equal to 0. Because we constructed the xy plane using the a and b vectors, az and bz are equal to 0. So these two terms, okay, these two terms are equal to 0. We don't have the z components for the a and b vectors. So because this vector, the resultant vector a plus b plus c is equal to 0, this component is 0, this summation is 0, and this summation must be 0. So this one, cz times az, must be 0, and finally the value of the cz must be 0. We can conclude that if we have this equation, the a and b and c vectors are coplanar. You know that the a vector x, y, z is equal to 0 if and only if all elements of this vector are equal to 0. Okay? So the next case, if we have four vectors, what if we have four vectors? In this case, again, we can write these equations. These terms are 0. Again, the az is equal to bz equal to 0, and we can write this equation. In this case, cz plus dz is equal to 0. So we can consider arbitrary numbers for cz and dz. These are not necessarily to be 0. Okay? So, for example, we can consider this plane, the AB plane, okay? And we can consider a perpendicular vector, C and D. The summation of the C and D is in AB plane, okay? But we have Z components for these two vectors. So in this case, no, A, B, C, and D need not to be coplanar, okay? This is the solution of this problem. So let's go for the next problem. Problem 15. Three vectors extending from the origin are given as R1, R2, and R3. We have x, y, z coordinates of these points. Find a unit vector perpendicular to both R1 and R2. Yes, we know that the cross product of R1 and R2 is a vector that is perpendicular to both R1 and R2. Here you can see this figure. This is R1, R2, and U1 is the cross product of the R1 and R2. Then we can make it normalized. Yes, by dividing this expression, right, to its norm, this vector. Part B, a unit vector perpendicular to the vectors r1 minus r2 and r2 minus r3. So again, we have a similar equation. We have coordinates. We can calculate r1 minus r2 and r2 minus r3. And then using this equation, we can calculate the normal unit vector to these two vectors, this expression. So let's check the numbers here for this problem, problem 15. This is the solution of the part A. In exam, you should use the formula, the determinant formula to calculate this cross product. Here I calculated this cross product using MATLAB. I wrote this code to save the time. This is R1, R2, R3, the part A of the problem. U1 is the cross product of the R1 and R2 divided by its norm. So what is the value of the U1? 0.08.41.9. Correct. And what is the next part? Here I visualized vectors. You know these functions. In the part B, we have R1 minus R2 and R2 minus R3. These two vectors. You know the definition. We used this definition in the previous problems. If this is the point I and this is the point J, what is this vector? The vector from the I to the J. This is Rij. That is Rj minus Ri. This definition. So here we have these two vectors. Again, we calculate the cross product and then divide by the norm. So this is u2. You can check numbers. Okay, for the part B, correct. And what is the next part of the problem? The part C, the area of the triangle defined by R1 and R2. So how much is the area? I mean this triangle. Let me copy this figure. Yes. How much is the area of this triangle? You know that the area is equal to 1 divided by 2, the amplitude of the vector, the cross product of these two vectors. Yes. So here I implemented this equation. You can calculate it manually. What is the area for the part C? 1 divided by 2, norm of the cross product of these two vectors is equal to 30.3. 30.3. Okay, this number, part C. And finally, the part D, the area of the triangle defined by the heads of R1, R2, and R3. So we have 3 points. We should construct a triangle with these 3 points and calculate the area of the triangle. So consider this 2D case. If we have these points, R1, the point R2, point R3, I can consider these two vectors, these two edges of the triangle. Okay, so this is R1, 2, and this is R1, 3. The area is 1 divided by 2, amplitude of the cross product of these two vectors. Okay, so I implemented this equation here. 1 divided by 2 amplitude of the cross product of these two vectors that are actually two edges of this triangle. You know that you can consider two edges and calculate the cross product of the vectors, right? Derived considering two edges of this triangle. So yes, you can run this M file to visualize the vectors and check your hand calculations with the MATLAB results. Anyway, let's go for the next problem. Problem 16. In geometrical optics, the path of a light ray can be treated as a vector having the usual 3 components in a rectangular coordinate system. When light reflects from a plane surface, the effect is to reverse the vector component of the ray that is normal to that surface. So here, if we consider this surface, consider a 2D case. This is a surface, and suppose we have this normal vector for this plane. If we have this light ray, we can model it as a vector. For example, V. Okay, it has 3 components, and this is the light ray after reflection from this surface, V prime. So the effect is just to actually the tangential components are the same for the incoming wave, the incoming light ray, and the outcoming one, but we have a reversion in the value of the normal component. Actually, here for the vector v, we can decompose it into two components. One component is this one, is this one in this direction, and another component is this one. Okay, so this is the vector v. I consider this point. It has one component that is normal to the end vector, or that is tangent to the plane, and a vector that is normal to the plane. Okay, so this is the component of the v prime, these two. As you can see, tangential components are the same on the surface, but we have these two normal vectors in opposite of each other. Okay, the effect of reflection. This yields a reflection angle that is equal to the incidence angle. So if we consider this is V tangent and this is V normal. This is V prime tangent and this is V prime normal. So V tangent is equal to V prime tangent, and V normal is negative of V prime normal to the surface. So if we consider these two equations, these two angles, theta 1 and theta 2, are equal. Okay, these two angles are equal. Using a vector representation in rectangular coordinates demonstrate that what happens when a light ray reflects from a corner cube reflector consisting of three mutually orthogonal surfaces that occupy, for example, xy, xz, and yz plane. The ray is incident in an arbitrary direction within the first octant of the coordinate system and has initially negative x, y, and z components of travel. So this problem says that if we have a cube and if we have a corner cube reflection, the reflection occurs at the same time considering these three planes. So what is the relationship between the v prime and v? So in this case that we have this, how we can find a relationship between v prime and v? V is a vector, is a, if I consider a column vector, is 3 by 1, and v prime is also 3 by 1. Can we have a transformation matrix here that is 3 by 3 that relates v prime to v? Or actually this matrix R, transformation matrix. So for this problem, we can find this matrix, not too complex. We had this problem 13, okay, how we can decompose a vector f, on vector g, considering a parallel component and a normal component. So here, in this case, I am going to find the relationship. We have the vector v, v tangent, this one. This is normal to the n vector. This is v that is normal to the vector n. and Vn is V that is parallel to n. What is the value of this vector? You know that is V dot n times n. So the tangential one will be equal to V minus V dot n times n, the normal one. So V prime is equal to, the tangential components are the same, is V minus V dot n times n. The normal components are in opposite directions. This is minus, the normal one is V dot n times n. So in total, V minus 2 times V dot n times n. Okay, so if we consider this transformation, we have V prime that is equal to R times V, and this is R. Yes. So we can construct the reflection matrix. Yes. The reflection matrix, we can construct that to have a relationship between the V and V prime. If we consider this coordinate system X, Y, and Z, so this is XY plane, this is YZ plane, and this is ZX plane. So what if we have a reflection simultaneously on these three surfaces? You know that we have three transformation matrices. So we have R1, R2, R3. We have three reflections. So this is the incident ray, and this is the out, right? The ray after the reflection. So you can prove these three transformation matrices. Okay, for example, what is the reflection for the xy plane? For the xy plane, we know that the normal vector is 0, 0 and 1. So here, if I consider this equation, this will be the vector v minus 2 times v dot n. V dot n is equal to, this is 0, 0, 1. This is v, and excuse me, let me delete this one. This is the normal vector n. The reflection from the xy plane will be equal to the vector v minus 2 times v dot n times n. V dot n is v3. This is 2 times vz, the z component, times this one, 0, 0, 1. Okay, so we have this actually. If I write this vector also in terms of its component, vx, vy, vz minus this one, 0, 0 minus 2 times vz. This is equal to vx, vy, negative vz. So what is the transformation matrix? In our case, we have reflections for these three surfaces, these three matrices we have. If we consider incident wave V equal to negative AX, negative AY, negative AZ, the ray is incident in an arbitrary direction in the first octant and has initially negative X, Y, and Z components. So the reflected ray is negative V in opposite direction. Okay, so interesting problem, not too complex. The corner cube flips all three Cartesian components of the ray, so the outgoing ray is exactly the negative of the incoming one. So, okay, I modified these notations for reflection matrices Rxy, Rzx, and RYZ. This notation is better. Yes, reflection with respect to xy plane, the zx plane, and the yz plane. Anyway, so let's go for the next problem. Problem 17. Point A and two vectors RAM and RAN define a triangle. So we have this point A, okay, and two vectors are given. This vector RAM, this is the point M, and this vector RAN. Okay, so find a unit vector perpendicular to the triangle. You know that the cross product of the RAM and RAN is perpendicular to both RAM and RAN. So we can use this cross product to find a vector perpendicular to the triangle, and then we can make it normalized. So this is the resultant unit vector. Part B, a unit vector in the plane of the triangle and perpendicular to RAN. So how we can calculate this vector? This is in the plane of the triangle, but this one is not. This is perpendicular to the triangle. And this red vector must be perpendicular to this vector RAN. So how we can calculate this? As you can see, this red vector is the cross product of the RAN and this unit vector that we calculated in the part A. So the unit vector perpendicular to RAN and available in the plane of the triangle is this cross product. Then we can make it normalized. This is the resultant vector. Part C, a unit vector in the plane of the triangle that bisects the interior angle at A. So how we can bisect the angle A here? This is our triangle. Okay, we know that we can bisect this angle knowing two unit vectors. A unit vector in this direction, yes, this is unit vector in the direction of RAM, and this is a unit vector in the direction of the RAN, this unit vector. Summation of these two unit vectors bisects the angle A. So this angle is equal to this one. Okay, so we can calculate this unit vector using this expression and then normalize it. First, we need to calculate these two unit vectors. Okay, and then we can calculate this expression. So here in this figure, you can see these vectors. The red one is the RAM The blue one is RAN. The purple one is the U1. The unit vector calculated in the part A. The black one is the unit vector calculated in the part B. And the green one is the unit vector of the part C. I wrote this M file to save the time. So here you can see the MATLAB for solving the problem 17. This is the point A. These two vectors are AM and RAN. This is the calculation of the U1. I implemented this equation, U2 and U3. First, I calculate these two unit vectors as I explained. Okay, and then we calculate the summation and normalize it. Then we visualize these vectors. So if I run this code, you can check the vector diagram. Okay, the purple one is perpendicular to the plane of the triangle. The black one is perpendicular to RAN, and the green one bisects the angle. Okay, perfect. So you can generate this interesting vector diagram in MATLAB using this M file that is the solution of this problem. So let's go for the next problem. Problem 18. Given two fields in spherical coordinates E and H, okay, evaluate S that is equal to E cross H and express the result in rectangular coordinates. B. Determine S along the X, Y, and Z axis. So as you can see here, the vector field E is in the direction of theta only. We have a theta component. You can see this spherical coordinate system. This is the theta angle. This is the phi angle. And we have these three unit vectors. So the vector field H is in the direction of the phi, and it is a function of theta, the amplitude of the vector, and r. So here S is the pointing vector. We will discuss it in detail in the next chapters. That is equal to E cross H. We can calculate this cross product in the spherical coordinate system and then calculate the x and y and z components in rectangular coordinates. So here is E and this is H. E cross H is this one, this vector. Cross product this vector that is equal to AB divided by R to the power 2 sine of theta to the power 2 A theta cross A phi. What is the resultant vector? Here you can see A theta cross A phi is A R. Okay, so you know that we discussed these details in the chapter. So you should review the chapter and review these two important coordinate systems that we have, cylindrical one and spherical. So here is the value of the S vector field. We have only component in the radial direction. Anyway, how we can calculate the value of the S along X, Y, and Z axis? You know that, for example, in a 2D case, for this coordinate system, x and y, for an arbitrary vector v, we have these two components, vx, and this is vy. We can decompose it into these two components. You know that vx is v dot ax times ax, and vy is v dot ay times a sub y. So actually, how we can calculate vx and vy? When we have a vector field v that is equal to vx ax plus vy ay, when we use the dot product for both sides of this equation, for example, for the ax, if I use dot product here, dot ax, and dot product here, ax, for this expression, so v dot ax is equal to vx ax dot ax plus vy ay dot ax. We know that this is an orthogonal coordinate system. So this is 0, this is 1, and Vx is equal to this one, the amplitude. And in the vector format, you should multiply that by Ax. So here, Sx is S dot Ax, that is equal to this one. And we have two important tables. You remember these two tables from the chapter 1, coordinate systems. We have a cylindrical coordinate system and a spherical one. So this table 1 1 is the dot product of unit vectors of the rectangular coordinate system with the cylindrical one, and table 1 2 is the dot product of the unit vectors of the rectangular coordinate system and a spherical one. So these two tables are very important, and you should remember these two tables for the exam. So here ar.ax is this one, this product. So we calculated the x component of the vector field S. Similarly, we can calculate S sub y and S sub z. Okay, y and z components. So you remember how we calculated this table during the course. You should review the chapter anyway. So let's go for the next problem. Problem 19. Consider the important inverse square radial field expressed in spherical coordinates f equal to a divided by r to the power 2 times ar, where a is a constant. So here we have this vector field f that it has only the radial component. A transform the field into cylindrical coordinates. B transform the field into rectangular coordinates. So not too complex. First, I am going to answer the part B, and then we answer the part A. So here, this is the f, that is a divided by r to the power 2 times ar. You know that the unit vector in the radial direction for the spherical coordinate system is this one, x divided by r, ax plus y divided by r ay plus z divided by r az. So simply, instead of AR, you can replace this summation. And what is the value of the R? Is a square root of the x to the power 2 plus y to the power 2 plus z to the power 2, distance of the point from the origin. Okay? So these three equations are used for changing the coordinate of the point from the xyz coordinate system to r theta phi, the spherical one. So yes, this is the resultant vector field in the xyz coordinate system. So let's check the solution for this problem. Problem 19. This is the vector field in the rectangular coordinate system. Here we have this vector field in the rectangular coordinate system. F, we have it here. And how I can calculate F rho, F phi, and F z in the cylindrical coordinate system like before. F rho is F dot A in the direction of the rho. For the cylindrical coordinate system, you can see these unit vectors. You remember these unit vectors from the chapter text. So here we have this table and this dot product we can calculate. The z components are the same. We know that the z component for the rectangular coordinate system is the same as the z component for the cylindrical coordinate system. And what about the phi and rho components? If we calculate the dot product of this expression with rho, this expression, x times ax plus y times ay, okay? So let's calculate the dot product with a rho. This is equal to a x dot a rho plus y ay dot a rho. So this is equal to cosine of phi ax dot a rho. So this is cosine of phi, and this is equal to sine of phi ay dot a rho. So this is sine of phi. And what is the value of the x? You know that this is x, y, and this is rho, this is phi. X is equal to rho times cosine of phi. So rho times cosine of phi, and the y is rho times sine of phi. So this is equal to rho times cosine of phi to the power 2 plus sine of phi to the power 2. That is equal to rho. So this is the rho component. And here, according to this equation, rho is the distance of the point from the z-axis. Okay, we have x to the power 2 plus y to the power 2 is rho to the power 2. And you can prove that the phi component is 0 if you calculate the same, if you calculate the phi component. You calculate the dot product and prove that the phi component is 0. So this is the vector field expressed in the expressed in the cylindrical coordinate system. Okay, this one. A good problem, and you can practice that. Anyway, so let's go for the next problem. Problem 20. If three sides of a triangle are represented by vectors A, B, and C, all directed counterclockwise, show that the amplitude of the C to the power 2 is A plus B dot A plus B, and expand the product to obtain the law of cosines. So here is the vector diagram. We have three vectors that construct a triangle A, B, and C. Summation is 0, okay, because all directed counterclockwise. A plus B plus C is 0, and C is equal to negative A plus B. So if we use the dot product, C dot C is A plus B dot A plus B. This is equal to the norm of the C to the power 2. And if you expand the right hand side of the equation, we will have this one. A to the power 2, the amplitude of the B to the power 2, and this is the geometric definition of the dot product. The angle theta is the angle between the A and B vector. So we will have this equation. These are amplitudes. Also, you know that theta is 180 degrees minus alpha. And cosine of theta is the negative of cosine of alpha. Yes. So if you replace this in this equation, we will have the law of cosines. C to the power 2 is A to the power 2, B to the power 2, minus 2AB times cosine of alpha. Interesting. We used the geometric definition of the dot product to prove this equation. Okay, so let's go for the next problem. Problem 21. Express in cylindrical components, part A, the vector from point C to point D. So the x, y, and z coordinates, rectangular coordinates of 2 points are given, the point C and the point D. And we should calculate the components of this vector R, C, D in the cylindrical coordinate system. So, what is the point of this problem? You know that in Cartesian coordinate system in rectangular one, RCD is simply x, y, z coordinates of the point D minus the point C. But if we have the components in cylindrical coordinate system, can we subtract them like this to calculate this vector? No. Okay. So first we should calculate the coordinates in the cylindrical coordinate system for these 2 points, and then considering the point that the vector is attached to it, we can perform transformation. So a little bit more complicated than the rectangular one. As you can see here, this vector is attached to the point C. Okay, And this is directed from the point C to the point D. And what about the RDC? RDC is this one. In rectangular coordinate system, we know that RCD is equal to negative of RDC. But again, in the cylindrical coordinate system, we don't have this equation. Okay, so this is important. How we can perform the calculations in rectangular coordinate system? For example, this 2D case, this is x and this is y. Consider this vector that is attached to this point x0 and y0. So if I move this vector from here to here, for example, or from here to origin, as you know, there is no difference between these three vectors. Okay, so just we changed the values of the x0 and y0. But in rectangular coordinate system, this is possible. In cylindrical coordinate system, we have differences between this vector, and this one. Okay, for their coordinates. The value of the x0 and y0 is important. Okay, so these three vectors in the cylindrical coordinate system don't have the same components. So this is important. Here, for example, we discussed in previous problems how to transform a vector field that is expressed in the rectangular coordinate system to cylindrical one. Okay, so if we have this vector here that it has two components, yes, fy and fx, these are two components of this vector. How we can transform it into cylindrical one? We need to know the x and y coordinates of this point, the point that the vector is attached to it. So we can calculate this angle phi. This is the angle phi. And then we can calculate the components in the radial direction and in the tangential one. This is a phi and this is a r. You know that we discussed this multiple times. For example, f in the direction of the radial component, a rho, is equal to fx fx times the cosine of phi plus fy. Okay, this component times the sine of phi fy, and so on for fy. You can derive equation. We discussed it in the previous problems. So we should follow this logic. Here, as you can see, I calculated the rho phi, and this is z component in the cylindrical coordinate system. Here you can see this cylinder in this image, and the radius of this cylinder is equal to 3.61. The point C is on this cylinder. This dashed line is the z axis. So I calculated coordinates of these 2 points in cylindrical coordinate system. Excuse me, we have a typo error here. This is the point D. Okay, so as you know, the rho, the value of the rho is equal to a square root of x to the power 2 plus y to the power 2. Rho is distance of the point from the z axis. Phi is this angle, and z components are the same for cylindrical and rectangular coordinate systems. So we will have these two vectors. So now we can calculate RCD and RDC considering rectangular components. We have this subtraction. Simply we perform these subtractions to calculate these two vectors. And when we have RCD, now we can calculate the rho, phi, and z components in the cylindrical coordinate system, the part A of the problem. What is the rho component is RCD dot A rho. A rho is calculated for the point C. Okay, so we should use the phi angle of the point C. And I implemented this equation here. Okay, this is minus 4 times cosine of phi plus minus 6 times sine of phi. That is equal to negative 6.66. What about the phi component is RCD dot A phi. So you remember this is negative fx times sine of phi plus fy times cosine of phi. This equation, we used it in the previous problem. So here I implemented this equation. The important point is that we should calculate unit vectors of the cylindrical coordinate system for the point C and then perform this dot product. Okay? Unit vectors for this point are different from unit vectors for this point. For example, this is a rho and this is a phi. So here, let's check the numbers for the problem 21 minus 6.66. This one minus 2.77 and plus 9. The next part, a unit vector at D directed towards C. But before solving the part B, let me calculate components of the RDC in cylindrical coordinate system. This vector, we calculated RCD, and now I am going to calculate the RDC before calculating its unit vector and transforming it into the cylindrical coordinate system. Here I did the calculations. I calculated unit vectors for the point D. The phi angle is negative 104 degrees. As you can see here, we have these three numbers. Okay, these are different from these numbers. And also we don't have this relationship RCD is equal to negative R DC that we have for the rectangular coordinate system. Okay, so yes, this is an important difference. The part B, a unit vector at D directed towards C. So we should normalize RDC. Here we can divide this vector by its norm to calculate a unit vector in the direction of the RDC, and then calculate the rho, phi, and z components. So this vector is attached to the point D. We calculate unit vectors of the cylindrical coordinate system for the point D and then perform the transformation. So remember and practice this logic. For a coordinate system, when we are going to transform a vector from one coordinate system to another one, first we should look at the point that the vector is attached to it, calculate the unit vectors for that point, and then perform the transformations, perform the dot products. Okay, you know that. Finally, the part C, a unit vector at D directed toward the origin. So this vector R in the negative direction of the D, that is this one, we can make it a unit vector like this and then perform the transformation. The angle that we should use is the angle of the point D. Here I did the calculations and you can see the values here. Okay. So as you can see here, for this unit vector, we don't have the phi component. Why? Because here we have this vector, okay, from the point D toward the origin. So as you can see, this vector is in the radial direction, right? Is in the direction of the A row. We should have a negative sign toward the origin. So the A phi component is 0. This is obvious, okay? So yes, you need to do the calculations and practice. Here you can see the vector diagram, the C vector, D vector, and R, C, D. In MATLAB, here I wrote this code, so you can run this code and practice. Here we have the point C, the point D, and RCD, RDC in rectangular coordinate system. Here I defined this inline function to calculate the rho, phi, and z components. This is a transformation of a point to cylindrical one. What is an inline function in MATLAB? So you can define inline functions like this. F, for example, that is a function of x at sign x, for example, 2 times x minus 1. So now I can write f1. It will evaluate the value of the function. Also, x can be a vector, right? You can define expression and use components. Inline functions are good. You can write a clear code. So simply, this function gets a point x and transform it into a cylindrical coordinate system. So this is the point C in the cylindrical coordinate system, and this is the point D in the cylindrical coordinate system. So here I calculated unit vectors a rho and a phi for the point C. As you can see here, I used the angle of the point C and I calculated RCD, the rho component, and the phi component attached to the point C. Okay, these two dot products. And I did the same for the rest, so you can check the numbers here that I calculated. Okay, these numbers and compare with the numbers that we have here. Interesting. So if I run the code, here you can see these 3 vectors. Here you can see this dashed line. First, we need to calculate components, the unit vectors attached to the point that the vector is attached to it, and then calculate the components. Anyway, so you can run this M file and practice this important problem. This is a complex problem. Okay, so let's go for the next problem. Problem 22. A sphere of radius a centered at the origin rotates about the z-axis at angular velocity omega. The rotation direction is clockwise when one is looking in the positive z direction. Using spherical components, write an expression for velocity field v that gives the tangential velocity at any point of the sphere. So here we have this case. We have a rotating sphere. Okay, this is the axis of the rotation. And as you know, the linear speed, the tangential speed at the surface depends on the distance of this point from the axis of the rotation. If we consider cylindrical coordinate system, this is the z axis. Okay, so this is the top view. This is isometric view. You can imagine that in this case, the direction of the rotation is counterclockwise when we look it from the top view. But in the problem, the direction of the rotation is clockwise. So, how we can express this velocity field in cylindrical coordinate system? Okay, you know that in a cylindrical coordinate system, if we consider this as z axis and this is x, okay, so this is theta. If you consider this sphere, what is the distance? The radius here is, for example, let's consider r. The distance of this point from the z-axis is r times sine of theta. Okay, this distance. And what is the value of the tangential speed? You know that when we have this angular speed omega, this point rotates around the z-axis with the angular speed omega. The linear speed will be equal to the radius of the rotation times the angular speed is r times sine of theta times omega. So what is the direction of the rotation when we look from the positive z axis? The direction of the rotation is clockwise, is in this direction, okay? Is clockwise. So we have this negative sign here. This is a phi. So this is the velocity field. You should imagine that. Okay. So this one. In this case, when we look at from top view, this is counterclockwise, but we should negate it. Okay. Here in this case. The part B, derive an expression for the difference in velocities between 2 points on the surface that have different latitudes when the latitude difference is delta theta in radians. Assume that delta theta is small. So here we have these definitions. This is the equator and this is the latitude angle, different from this angle theta. So I call this theta star, or here I used this lambda. Okay, notation in notes. This is the latitude angle. The velocity field is negative of r times sine of theta, that is cosine of lambda, the latitude angle, and this is point of interest, times the angular speed times a phi. What is the amplitude of the linear speed? Is this one, the amplitude of this vector, r times cosine of lambda times omega. So let's calculate the derivative of the amplitude of the speed versus the latitude angle. Is this one, derivative of the cosine of lambda is sine of lambda, and we can approximate this differential with this fraction, okay, delta v divided by delta lambda. Finally, we can calculate the variation of the speed as a function of variation of delta lambda, the latitude angle for a small change. Actually, we linearized this equation, okay. So this is the equation, this is the approximation. When we have a small change in the latitude angle, we can calculate the variation in the value of the speed. As you can see here, when we approach poles, we have lower and lower linear speeds, and we have a maximum speed on equator, right? Because it has a largest radius of the rotation. So this is also obvious from the top view. And here, the next part of the problem, part C, find the difference in velocities 1 degree on either side of 45 degrees north latitude on Earth. Take the Earth's radius 6,370 kilometers at 45 degrees. So here we can calculate the difference in the value of the speed between these 2 points when we change the latitude angle from 44 degrees to 46 degrees. So here the midpoint is 45 and the difference is 2 degrees. We can replace in this equation. We have the radius of the Earth, this number. What is the angular speed of the Earth? We have one rotation in 1 day. Okay? So 2 pi divided by 24 hours times 60 minutes times 60 seconds. Okay? 1 day has 24 hours, and each hour has 60 minutes, and every minute is 60 seconds. So we can replace these two parameters in this equation and calculate the difference in velocities. So when the latitude angle changes from 44 to 46, we have this change in the value of the linear speed, negative 11.4 meter per second. An interesting problem. Also, I wrote this code in MATLAB for the problem 22 to visualize this vector field. Okay, so you can generate this image and try this code. For this vector field, I implemented the equation that we discussed in this problem. Okay, so anyway, let's go for the next problem. Problem 23. The surfaces rho equal to 3 and rho equal to 5, phi equal to 100 degrees and equal to 130, and z equal to 3 and 4.5 define a closed surface. So we have six surfaces in the cylindrical coordinate system, and these surfaces defined a closed surface. We have a geometry like this, okay? So we have these two phi angles, these two z levels, and these two rho levels. Okay, this is the geometry, the closed volume defined by these six surfaces in the cylindrical coordinate system. How we can calculate the volume? Not too complex. As you know, we have these expressions for the cylindrical coordinate system. This is the image C, the differential volume unit in circular cylindrical coordinate system. D rho, rho d phi, and dz. This is the volume element, the differential volume element. The length in the radial direction is d rho, in axial direction is dz, and in the circumferential direction is rho times d phi. So just we should calculate this triple integral d rho times rho d phi times dz, the differential volume. The value of the rho is from 3 to 5, the value of the phi from 100 to 130 degrees, and the value of the z from 3 to 4.5. I calculated the integral here. First, we can calculate the integral for the rho, that is rho to the power 2 divided by 2. We replace the numbers. Then for the phi, I calculated the difference. This is in degree. We should change it in the radian. And this is the integral for dz. The total volume is 6.28. Okay? So this is the part A, the volume. Part B, the total area of the enclosing surfaces. How much is the area of enclosing surfaces? As you can see here, we have six faces. Okay, we have a geometry like this. We have a geometry like this in this problem. So here we have these faces. This is the face number 1. This is the face number 2. The Z faces. The face for the phi 1. We have one face for the phi 2. This face. And this face for the rho 1. And this face for the rho 2. 6 faces. You can imagine that. So faces in the Z directions, these two faces, 1 and 2, have the same areas, right? This top surface and this bottom surface. These two faces have the same area. So we can write 2 times the surface element d rho times dz. Okay, the surface element here, if you consider this surface element, this is d rho, okay, times dz. Okay, excuse me, I am explaining this space for the phi constant and this one. So the element area, for example, this one is dz times d rho. The area of this face is the same as the area of this face. This face. Okay? So here we have this equation, this double integral. We have two faces, the bottom face and the top face. The areas are equal, but we have also these two faces, this one for the row 1 and this one for the row 2. The areas of these two surfaces are not the same, so we need to have these two separate double integrals, okay, considering different values for the row. I implemented these equations here, these two double integrals, and we can calculate this double integral to calculate the total area that is equal to 20.66. Not too complex, you can calculate these double integrals. The part C, the total length of the 12 edges of the surfaces. So yes, we have 12 edges. How we can calculate the total length? This is the geometry, okay, of this problem. And as you can see, we have these edges 1, 2, 3, 4, these 4 edges, 5, 6, 7, 8, and this one 9, 10, 11, 12. We have 12 edges. The lengths of red edges are the same. The lengths of purple edges are also the same. The lengths of these two edges are the same. And the lengths of these two edges also are the same. I calculated the total lengths here for the vertical edges. We have these numbers 4.1.5 for this red edge. These purple ones is equal to 4 times 2. 5 minus 3 is 2. We have 4 edges. 4 times 2, 4 times 4.5 and minus 3, that is 1.5, and the rest. The total length is 22.4. And finally, part D, the length of the longest straight line that lies entirely within the volume. So, yes, you know that the distance of this point from this point is the longest distance that we have. Okay, so we have these 2 points. Rho is equal to 300 degrees and z equal to 3. We can calculate x, y, z components. The second point has rho equal to 5, phi equal to 130, and z equal to 4.5. We can calculate the rectangular components, and finally we can calculate the distance between the point 1 and the point 2. Okay, that is 3.1. So, yes, we calculated numbers for 4 parts of this problem, this geometry. Let's go for the next problem. Problem 24. Two unit vectors a1 and a2 lie in the xy plane and pass through the origin. They make angles phi 1 and phi 2 respectively with the x-axis. So we have these two unit vectors in the xy plane. Okay, this unit vector a1 and a2 is this unit vector. This is phi 1 and this is phi 2. A Express each vector in rectangular components. Yes, a1 we can write cosine of phi1 times ax plus sine of phi1 ay, and a2 is cosine of phi2 ax plus sine of phi2 a sub y. Okay, we decomposed these two vectors in rectangular components. Take the dot product and verify the trigonometric identity, this identity. Yes, when we calculate the dot product, a1 dot a2, this is equal to the amplitude of vectors, the multiplication. We have unit vectors times cosine of the angle between two vectors, phi1 minus phi2, is equal to dot product. This is cosine of phi1 times the cosine of phi2 plus sine of phi1 times sine of phi2. Yes. So this is for the part B. And the part C, take the cross product and verify the trigonometric identity as this one. So yes, we can calculate the cross product, that is multiplication of amplitudes times the sine of phi1 minus phi2 times the az, the unit vector in the z direction. And this geometric definition is equal to this operational definition. If you calculate this determinant, we will have this. Okay, so we have proved this trigonometric identity using the cross product. So let's go for the next problem. Problem 25. Convert the vector field H into cylindrical coordinates. A is a constant. So we have this H, this vector field, that is equal to H is equal to A divided by x to the power 2 plus y to the power 2 x times A sub y minus y times A sub x. Okay, this vector field. How we can calculate this vector field in the cylindrical coordinates? We did similar problems before. So according to these equations, instead of x and y, we can use these two equations. Instead of x, if we consider this rho times cosine of phi, and instead of y, we can write rho times sine of phi. So the h will be equal to a divided by rho to the power 2 times here rho cosine of phi a sub y minus rho times sine of phi times a sub x. So here we can simplify this equation. We will have this equation h is equal to this. And how we can calculate h rho and h phi? We should calculate this dot product. When we have a vector field and we are going to calculate its component in an orthogonal reference frame. Okay, in an orthogonal coordinate system, we should take the dot product with unit vectors. So h dot a rho is this one. You know that ay dot a sub rho is sine of phi. Okay, according to this important table, table 1.1. You can remember these tables, right? Not too complex if you consider geometrical equations for this cylindrical coordinate system. You can remember these dot products. And here we have a sub x dot A sub rho is this one, cosine of phi, and h rho will be equal to 0. Okay, if you calculate this expression. What about the h phi? The h phi is this one. Okay, the h phi is this one. We should calculate the dot product of the h with a sub phi. That is equal to a sub y dot a phi. And here we have this dot product. You can replace these two terms here. A y dot a phi is cosine of phi, and this is negative sine of phi. So we will have this a divided by rho. So only we have the phi component. Excuse me, here we have a typo error. This is h phi, the h in the direction of the phi axis. Okay, so you can see the final expression, that is a divided by rho. We can visualize this vector field. Okay, let's try it in MATLAB for the problem 25. Let me save this, the problem 25. In this case, I am going to generate a mesh grid in cylindrical coordinate system. So here I write the rho and phi, generate a mesh grid by changing the value of the rho line space from, let's say, 1 to 5. Consider 10 points and change the value of the phi from 0 to 2 times pi. Consider 30 points. And x is equal to, first we should vectorize these two vectors, rho and phi. We vectorize them. X is equal to rho times cosine of phi, and y is equal to this one. Just I generated a grid for points that I'm going to calculate the vectors and plot the vector field. So if I plot x and y, just show points. So I use this syntax. Here, as you can see, we have this mesh grid in cylindrical coordinate system. And here again, we can write hold on, box on, and the axis equal. What is the value of the hx and hy? We have this expression. Okay, so consider a equal to 1. Hx is equal to 1 divided by x to the power 2 plus y to the power 2. Here we have negative y. So I should write a negative y here. This is hx. And what is the value of the hy? This is x. Okay. So finally, we can use the quiver function x, y, hx, and hy to plot this vector field. Yes, perfect. You can see the points of the mesh grid and the vectors. As you can see, we have only vectors in the phi direction, as we calculated here, h phi. H rho is 0. We don't have radial component. You can decrease or increase the mesh size by setting these numbers. For example, from 2 to 5, consider 30 points. You can handle the mesh grid size. Perfect image we generated with the MATLAB software. So you can try this simple M file that we wrote and generate this vector field. Anyway, let's go for the next problem. Problem 26. Express the uniform vector field 10 times a sub y in cylindrical components and spherical components. So, what is the value of the a y in cylindrical coordinate system? Is equal to sine of phi. Okay, so if we take the dot product of a y with the a row is sine of phi, its dot product with the phi is the cosine, and with z is 0. So a sub y is equal to this one, and if you replace here in this equation, this will be the expression of this expressing this vector field in the cylindrical coordinate system. What about the spherical one? Here you need to consider this row. Okay, a sub y is equal to sine of theta sine of phi times ar plus cosine of theta sine of phi times a theta plus cosine of phi times a phi. So you can replace it in this equation. So we will have expression in the spherical coordinate system. As you can see, here we have a simple expression in the rectangular coordinate system. And if we express it in a spherical one, it seems too complex, right? So depending on the type of the vector field, we can select the proper coordinate system. For example, in this problem, the proper coordinate system is cylindrical one, because these vectors are in the direction of the phi. And in this problem, the proper coordinate system is rectangular one. We have a uniform field in the direction of the y-axis. Okay, so you can review these topics, okay, and compare. So let's go for the next problem. Problem 27. The important dipole field to be addressed in chapter 4. We will discuss electric dipole in the chapter 4 is expressed in spherical coordinates as this one. So, we have this electric field generated by this dipole that is expressed in the spherical coordinate system. We have the radial component and the theta component only, where a is a constant and r is a positive number. Okay, this is the problem. We have a positive q charge on the z-axis here and a negative charge, equally negative one on opposite side on z-axis. The distance between these two charges is d. We will solve this problem in the chapter 4 to calculate the electric fields generated by these two electric charges, this electric dipole. Here you can see the case. We have streamlines of the electric field. Also, you can see the vectors, right? The electric field generated by these two charges, an important problem, okay, in the chapter 4. So this field is equal to this one, A, Identify the surface on which the field is entirely perpendicular to xy plane and express the field on that surface in cylindrical coordinates. So, where the field is entirely perpendicular, you know that for the xy plane, for the xy plane, the theta angle is 90 degrees. Yes, for the xy plane, this theta angle is 90. So let's replace it in this equation, theta. We will have this a divided by r to the power 3, 2 times cosine of 90 degrees times ar plus sine of 90 degrees a theta. So this is equal to 0 and we will have this. Yes, this equation a divided by r3 a theta. And you know that on xy plane a theta is in opposite direction of the z, az. So in cylindrical coordinate system, this is a divided by rho to the power 3 times az, the negative direction. So you know that we have this x and y. This is z on xy plane. This is actually the value of the r, the radius from origin, that is equal to rho. The value of theta is 90, and a theta is in this direction, az is in this direction, az in opposite direction. So this is the expression in the cylindrical coordinate system. Part B, identify the coordinate axis on which the field is entirely perpendicular to the xy plane and express the field there in cylindrical coordinates. Okay, in the part A, we calculated the field perpendicular to the xy plane. Here you can see the xy plane field vectors are perpendicular, and for this part we should find the axis. As you can see, the field, the electric field along the z-axis is perpendicular to the xy plane. Okay, we have two cases for the z-axis where theta is equal to 0 and where theta is equal to 180 degrees. Okay, so when theta is 0, we will have this field, and when theta is equal to 180 degrees, we will have this field. Yes, you can do the calculations. Perfect. Okay. So, what is the next part of the problem? Specify the surface on which the field is entirely parallel to xy plane. As you can see, according to this figure, we don't have a surface that the field is entirely parallel with the xy plane. For each surface parallel to xy plane, we have AR component and a theta component. So let's check solutions also for this problem. 1.27, you can see the solution of the part A and the part B. So let's go for the next problem. Problem 28. State whether or not A is equal to B, and if not, what conditions are imposed on A and B when A, we have this condition A dot AX is equal to B dot AX. So when we have this equation, when we have this condition, we can calculate the dot product. Actually, this equation corresponds to this one. We can conclude that ax, the x component of the vector a, is equal to bx. So vectors a and b are not necessarily equal. Okay, they can have different ay and az components. Using this condition only, we can say that the x components are the same. What about the next condition? A cross AX equal to B cross AX. In this case, we know that A cross AX is equal to A, the perpendicular component of A, on the x-axis. Okay, the unit vector. We discussed this case in one of our previous problems. And we have this unit vector ax, and we have this vector a. The dot product is this one, that is a parallel with ax, and the cross product gives this one, a that is perpendicular to ax. So in this case, we can write a perpendicular to ax is equal to b perpendicular to ax. Again, these two vectors are not necessarily equal. They can have different parallel components with the unit vector ax. The part C, if we have these two conditions at the same time, what is the situation now? When the cross product of two vectors with ax and dot products are equal with ax, yes, we can say that the vector a and b are equal. Okay, because in this case they have both the same parallel component and perpendicular component to ax. So two vectors that have these two equal components corresponding to this unit vector, yes, these two vectors are equal. And the part D, if we have this condition a dot c is equal to b dot c and a cross c is equal to b cross c, where c is any vector except c equal to 0. If we have these two conditions in general for an arbitrary vector c that is a non-zero vector, yes, the vectors a and b are equal. You can prove that. Here is the proof. We have a cross c equal to b cross c. So let's collect all terms on the left hand side. A cross c minus b cross c equal to 0. A minus b cross c is 0. So as you know, when the cross product of two vectors is 0, those vectors are in parallel. So we can write a minus b is a constant number lambda times c. So now let's use the dot product. We know that a dot c is equal to b dot c. So a minus b dot c is equal to, let's replace this term here, lambda c dot c. That is equal to lambda times the amplitude of c to the power 2. Because the c vector is non-zero, it has the amplitude that is higher than 0. And according to this equation, the lambda must be 0. And here you can conclude that in this case, A is equal to B. So, yes, Good question, good problem. When we have these two relationships at the same time, we can prove that the vectors A and B are equal. So you can review this problem. Let's go for the next problem. Problem 29. A vector field is expressed as f that is equal to a z a z. This is expressed in the rectangular coordinate system where a is a constant. Evaluate the components of this field that are normal and tangent to a spherical surface of radius a. Express all results in spherical coordinates and components. So, yes, again, we have a vector field f, and we are going to calculate the components in the spherical coordinate system, the normal and tangential component. So here we have fr. The radial component is f dot ar, or az dot ar. What is the value of the dot product of the az and ar? Is cosine of theta. Okay, so here this is cosine of theta, and the z component is equal to r times cosine of theta. The radius of the spherical surface is given. It is equal to a. Instead of z, we can write a times cosine of theta. Okay, so the radial component is a times the capital A times a times cosine of theta to the power 2. What about the theta component? Is f dot a theta. Again, we have this equation az dot a theta is equal to negative of sine of theta, this expression. What about the phi component? The phi component is 0 because az dot a phi is equal to 0. So only we have radial that is normal to the spherical surface, and this theta component that is tangent to the face. Yes, the vector field is uniform in the direction of the z-axis, and we can decompose it into theta component and the normal component to this face. Let's go for the next problem, that is the last problem of the chapter 1. Problem 30. Consider a problem analogous to the varying wind velocities encountered by transcontinental aircraft. We assume a constant attitude, a plane Earth, a flight along the x-axis from 0 to 10 units, no vertical velocity component, and no change in wind velocity with time. Assume AX to be directed to east and AY to the north. The wind velocity at the operating attitude is assumed to be equal to this one. So the velocity field is given. Actually, we have this xy plane, and the airplane moves in x direction. So this is the airplane. You can consider this, that moves in x direction above the xy plane. Okay, and we don't have the z component of the velocity. The travel length is from the 0 x to 10 units. Okay, we have x component of the velocity and the y component. So here you can see the direction of the movement in the direction of the x-axis, and this is the y-axis. Determine the location and magnitude of A, the maximum tail wind encountered. So this is the tail wind, the direction of the wind velocity in x direction in the positive of the x direction. So from 0 to 10, that is the x travel length, where we have the maximum positive x, the maximum positive Vx. I generated this plot using the MATLAB. Also, you can find maximum of this function ax for a constant value of the y coordinate. I considered y equal to 0 in this case. So as you can see, we have maximum tailwind speed when x is equal to 10. And when x is equal to 4, we have this local minimum. Okay, we have this local minimum, and the maximum is for x equal to 10. The next part, repeat for, the part B, repeat for head wind. So this is the headwind, the x component of the velocity field in the negative direction of the x-axis. As you can see here, the Vx component is always positive. So the x component is always positive, and so therefore no headwind exists over the travel length. Yes, because the headwind is in opposite direction of the movement of the plane, the airplane. So the next part, the part C, repeat for the crosswind. The crosswind is the velocity in the direction of the y-axis, in this direction, Vy. So we can plot the Vy versus the travel length, this function. Okay, this function, you can extract the y component, change the value of the x, and plot the Vy. So where we have the maximum Vy is when the x is equal to 0 at the start of the movement. Here we have the maximum Vy for this cross wind. And the part D, would more favorable tail winds be available at some other latitude? So if we change the y here, in this case, the movement is on x-axis when the value of the y is equal to 0. But if we have movement here for a different latitude angle, yes, or here, so according to this equation here, as you can see, we have the maximum wind when the y is equal to 0. When we change the latitude angle, the value of the denominator will be higher, and we will have lower velocity fields. The latitude associated with y equal to 0 gives the strongest tail wind. Yes, this is obvious. We have y to the power 2 in the denominator here. I generated this vector field using the MATLAB, and as you can see, when the value of the y is 0, we have highest velocities here. And as long as we increase or decrease the value of the y, we have lower and lower speeds. okay, for different latitude angles. So here you can run this M file for this problem. I defined these two handle functions to calculate Vx and Vy and generated these two plots, variation of Vx and Vy along the travel lengths, and this is the vector field, the speed vector field in this problem. Anyway, we completed all problems of the chapter 1, and I hope you found this video useful in your exam. And let's continue solving the problems of the chapter 2 in the next video.